Hello everyone. Today I would like to show you an experiment done by great scientist Galileo Galilei which contradicted the view of Aristotle, who said that rest is the natural state of an object. So for this experiment we need two frictionless planes and a smooth marble. When we release the marble from one side, it rolls down, gaining in acceleration, and then travels to the second plane where its velocity reduces. Now, if you observe the situation very carefully, we would see that the marble always climbs up to the same height from which it is released. When we reduce the angle of inclination of the second plane, we would see that the marble still travels to the same height from which it is released, but then the marble has to travel a longer distance for a longer time. Now, if we reduce the angle of inclination of the second plane to 0, that is, we make the second plane flat, how long the marble will have to travel in order to reach its initial height? Its answer would be that the marble would travel forever and forever, indefinitely, with the same velocity, yearning to reach the same height from which it was released, unless and until acted upon by an external unbalanced force. This made Galileo deduce the inertia of motion, which states that if an object is in motion, it will continue to remain in motion with the same velocity unless and until acted upon by an external unbalanced force.
Dear all viewers, welcome to the demonstration of Newton's third law of motion. I am Gulrish Khan of class 9th G. I am here to demonstrate Newton's third law of motion using a working model. Now, I have made this model using a balloon, a straw, a paper and some wheel. The paper I've chosen is a thin paper so that the car moves. Now, what happens as the car moves? The balloon pushes the air backwards. As the balloon pushes the air backwards, the car moves forwards. The rocket car is proportional to the flow according to the principle of Sir Isaac Newton's third law. When the balloon pushes air backwards, the air pushes the balloon and this car starts working. Now, let me show you a demonstration of it. Now, as you can see, I have inflated the balloon, and as I release it, the air will be pushed forward, and as the car is attached to the balloon will push air backwards and the car will move forward.
Have you ever wondered how roller coasters work or how they move so fast? Well, it is not an engine. Roller coasters are actually based on Newton's 3 laws of motion, and I'm going to be demonstrating those 3 laws with the help of my model of a marble roller coaster. I'd like to begin by stating the first law of motion, which states that if a body is at rest or in motion, then it will continue to remain in rest or in uniform motion unless and until an external unbalanced force acts on it. I've made the tracks of a typical roller coaster, and instead of a marble, we're going to take an iron ball. I'm going to release this from that height, and then let's see what happens next. At first, it might seem impossible to think that the ball could cover all the distance. But we have the ball right here. Now we wonder how the ball manages to go all around the track. This happens due to Newton's first law of motion, also known as law of inertia. In real roller coasters, the train at the beginning is at rest, and then it is pulled by a motorized chain to the top hill, where the force of gravity acts on it. Here too, the external force of gravity acts on the ball. As we saw that the ball moved very smoothly without having any obstruction in its path. The inertia of motion of the ball is what is very much perceptible to us. Now, as we all know that gravity is the downward pull of the earth that attracts objects towards the center of the earth, then why doesn't this gravity work on here in this loop? As per gravity, the ball should have dropped. But the ball goes round the loop. This happens because the ball's inertia overcomes the force of gravity, which helps it to go round the loop and around the track. Now let's come to the third type of inertia, that is inertia of direction. As you can see, there are barriers made to change the direction of the ball. Otherwise, the ball would have continued to move in the same direction of its motion. It is the same with real roller coasters. As the ball is released, the gravity increases the velocity of the ball, which in turn increases the momentum. As the momentum changes with time, it also brings a change in the force acting on the ball. Here, the second law of motion applies to the model. The second law of motion is defined as the force acting on a body is directly proportional to the rate of change of momentum. As we all know, force is equal to mass multiplied by acceleration. The change in acceleration is brought by gravity. Also, the change in mass brings a change in the force acting on the body. We tried with different balls of different masses, and each ball has different momentum. This is an iron ball, which is the heaviest of them all. Then we have a rubber ball, which is lighter than the iron ball. And the last we have a plastic ball, which is the lightest of them all. Now, as we saw that all the three balls had different momentums and were able to cover different distances. So, the second law of motion given by Newton applies to roller coasters and also in this model. Now, if we were to say that only the force of gravity was acting on the ball, then the ball should have pierced through the track, but that is not the case. This means that a force is being applied on the ball such that the ball is still and is not going down due to the force of gravity. This is the third law of motion.
And today I am presenting an activity with the help of a working model to demonstrate Newton's three laws of motion. So, this is a balloon-powered vehicle, and this works on the principle of Newton's third law of motion. When air comes out of the balloon, it exerts an equal and opposite force on the balloon, which makes the vehicle move. Like this. Now, this passenger has fallen down the vehicle and he may also suffer from injuries. This is because of his body's inertia of motion. This is Newton's first law of motion. As you can see, there is a bumper in the front of the vehicle. This is the bumper. A bumper acts as a shock absorber. The rate of change of momentum decreases due to the bumper, thus protecting the vehicle from any kind of damage. Thank you.
Today I am here to demonstrate my model based on Newton's third law of motion. I'd like to demonstrate Newton's third law of motion with the help of my working model. I'll take this ball, I'll place it here, and then I'll pull my slingshot to approximately 20 centimeters in length. And then I'll leave it. As you saw, when I pulled the slingshot approximately 20 centimeters back, the ball went, it hit the target and came back approximately 20 centimeters. This proves the Newton's third law of motion that every action has an equal and opposite reaction. Because the slingshot's action was approximately 20 centimeters,
The ball hit the target and came back 20 centimeters in the opposite direction of its action. Hence,
Good morning, ma'am. Today, I, Aditi Sharma of class 9th E, rule number 4, is here to show you some daily life practicals on the topic the Newton's first law of motion. So now, let us see one example now. Here, I am having a tablecloth and now I am going to pull it. Now let's see what would happen. So let's go. Oh, what happened? The object, like this container, remains in their place or move a little but didn't fall. Why? Because they are in the inertia. So now, let us see one more example. So, here I am having a bat which is act like an external force, and here in the form of dust is the wheat flour. So let's see what will happen in this. Now I'll beat it once. Now let's see what happens. Oh, the dust come out. Why it does come out? The dust was in the inertia of the rest. Now the particles of dust are in the form of inertia of motion.
In this video, I am going to show a working model on Newton's third law. That is, every action has an equal and opposite reaction. This is the third law which Newton stated, that every action has its equal and opposite reaction, as now we can see in this video.
Good morning to ma'am. Today I am Devyanshi Verma of class 9th F is present before you to present my working model of physics. So for this we will go far away from our earth to our very own universe to understand this concept, as we have large masses in our universe. So here you can see is our solar system. We have our sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All of these comprises to form our solar system. So, as we all know that the revolution of the earth around the sun on its orbit is because of the gravitational force applied by the sun to the moon. But as we studied in physics, the third law of motion states that for every action there is an equal and opposite reaction. So when the sun is applying a gravitational force to the sun, to our earth, the earth will also apply a gravitational force of same amount on the sun. So the mass of the sun is comparatively very large to the mass of the earth. So the effect of the earth's alone gravitational force cannot be noticed in the sun. But the sun does apply gravitational force on all these objects in all the planets in our solar system. So when the gravitational force that is equal and opposite to the force applied by the sun on our planets comprises, and the sum of all these forces of all the planets is when opposing the force of the sun, there is a movement that can be seen and noticed in the sun, that is the wobble effect, also known as the Doppler effect. So the sun wobbles at its place. So in this we can clearly see that for every action, that is the force applied of the gravitational force applied by the sun on all these planets with an equal and opposite reaction, that is all the gravitational force that is applied by all these planets on the sun. And the sun wobbles and the planets revolution around the sun. So here it is proved that the third law of motion, for every action there is an equal and opposite reaction, is proved with such a big masses, and both action and reaction is noticeable when we take example of our own solar system. Thank you. I hope you liked my video.
A very pleasant evening, respected ma'am. Today, I, Khyati Maurya of class 9E, is here demonstrating my model on the topic force and laws of motion. So this is my model. My model is made up of wooden plank of wood connected with softwood framework. And these frameworks are connected via thread. These threads are in connection with the marbles. These marbles and thread I have connected using glue gun. The first law of motion states a body tends to remain at rest or move with uniform motion in a straight line until and unless an external force is applied. In this case, let these marbles be the object and my hands an external force that I am going to apply on these marbles. So this I applied and they start moving. This is also called law of inertia. The greater is the mass, the greater will be its inertia. Let's move to the second law of motion. The second law of motion states the net force acting on a body is directly proportional to its rate of change of momentum. Momentum is mass into velocity. So let this and this marble, these marbles have equal masses, and its velocity be u and its velocity be v. So the delta of these momentum will be p of f minus p of u upon t, which gives us m into v minus u upon t. We also know v minus u upon t is equals to acceleration. So we can also write force is equals to mass into acceleration. Let's demonstrate it using my model. Suppose if I accelerate it only this much area, let's see what happens. It moves, but only a bit. But if I accelerate it much more, it moves much more. That proves force is directly proportional to mass and force is directly proportional to acceleration. Let's come to the third law of motion. The third law of motion states to an object there is always an equal and opposite reaction. A very common example for this is when an accident between truck and car. Always the truck driver is blamed for it. But the force that they apply on each other is equal. But due to the mass of truck, the truck driver is blamed. Let's demonstrate it using the model. Let these be on rest first and then move this. This marble also moves with the same force. This proves that every action has an equal and opposite reaction. If I accelerate these two will also move with the same force. And these continue to move until and unless they balance each other. Let's demonstrate it one more time. They continue to move. This was all about the three laws of motion. I hope I made it very clear in explaining it. Hope you like it.
You